All right, in this presentation, I'm going to be talking about the second part of the quantum mechanical model notes. This presentation is specifically going to be focused on electron configurations. So, how electrons fill those orbitals that were discussed in the last set of notes. So first, as a quick refresher, remember that we have a couple different types of orbitals, some of which are shown on screen. Remember, these orbitals are places that we would expect the electron to be most of the time. We can see up here on the top section, we have our s orbital. We can see in the middle section here, we have our different p orbitals. There are 3 different p orbitals. And on the bottom, we have our 5 different d orbitals. And so each orbital can hold a maximum of 2 electrons, and we'll explore why that is in this presentation. Also note there are f orbitals as well, but we're not going to talk about them here because they're a little more complex than what we need to get into. So let's first remind ourselves about the Bohr model. Just like in the Bohr model, our orbitals are going to be filled from the lower energy levels to the higher energy levels. In the Bohr model, this looked like filling the first ring with 2 electrons, the second ring with these 8 electrons, the 4 pairs, and our outer ring, our third ring, with 4 pairs as well. And we could keep going with the Bohr model and fill more and more rings. But specifically, we're going from the low energy levels close to the nucleus to the higher energy levels away from the nucleus. The same thing is true with our orbitals in the quantum mechanical model, but there is a sort of pattern. However, it's not as clean as what I've shown here. Here at the bottom, this is sort of true, but sort of not true. We don't just go from one set of orbitals to another, they actually end up repeating, and we'll see how we can use the periodic table to predict that pattern. However, we also have a pretty nice chart. And we can see that the principal quantum number, remember that's the number that goes in front of the orbital, typically orbitals with lower principal quantum numbers have lower energies. This is almost always the case. We can see in the chart the 1s orbital has less energy than the 2s orbital, which has less energy than the 2p, but these 2p's and 2s's, they're the same principal quantum number, and they're kind of at similar energy levels. Regardless, they're both lower than what comes next, the 3s. So in general, that number out front tells us kind of about how much energy an orbital has. 1 is lower than 2, which is lower than 3, and so on and so forth. And this corresponds pretty much to those n values we used for the Bohr model, saying what each shell was away from the nucleus. We can also see that that s orbital, the 1s orbital, it's the same kind of orbital as what gets filled next. We fill a sphere, and then we fill the 2s orbital, which is actually a slightly larger sphere. We would then put electrons in the 2p orbitals, all 3 of them, and we would then start filling the 3s orbital, and we have this sort of pattern emerging. We'll talk about that more on this slide. In general, orbital energy increases from s orbitals to p orbitals to d orbitals to f orbitals, but it's a little more complicated. Before we go any further, just a reminder, electrons are most likely to be in the lowest energy state unless somehow they gain energy. Say if we heat them up or we put electricity through them, they're going to be in that lowest state, which is how we'll fill them. Also, just like with the Bohr model, these energy levels are slightly different from one atom to another. The pattern will always stay the same for our orbitals, 1s, 2s, 2p, and so forth. But these gaps and where these different orbitals are located, it might be slightly different depending on what atom or what element we're talking about. So let's establish a quick relationship between the Bohr model and the quantum model. Notice that my 1s orbital, the smallest orbital, and what you have up here, that's going to correspond to this first Bohr shell. We can see we have a paired set of electrons here, and we know that each orbital can fit 2 electrons. So it's basically showing that in my Bohr model. As I go further, I would fill the 2s orbital and all three 2p orbitals, given that each one of these, the s, px, py, pz, considering that each one can fit 2 electrons, it makes sense that the second shell, the 2s and all the 2p's, can fit a total of 2, 4, 6, 8 electrons. So the 2s and 2p, they do correspond to this second shell of the Bohr model. And we could continue this pattern on. In our next ring, our next shell, the 3s orbital, would be the two first electrons in our Bohr model. Now this might seem odd, the fact that we have unpaired electrons and this single orbital. If those electrons were close, we would expect them to be paired. More on this at the end of the presentation. So we actually have a tool that helps us see this pattern. You don't have to memorize which orbitals are filled in which order, as long as you remember how to use your periodic table. We're going to read this from top to bottom and left to right, and that will show us what orbitals fill in what order. First, we fill the 1s orbital going from left to right. We would then go to the second row and we'd fill the 2s orbital, and then the 2p orbital, and then the 3s orbital, and we would continue this pattern. And I show in this GIF the first couple sets of orbitals and how they would fill. We start at the top and we fill from the top to the bottom and the left to the right. So keep this pattern in mind. You will always know the pattern of orbitals as long as you know your periodic table. Now, let's talk about how to construct an actual electron configurations. These electron configurations show which orbitals contain electrons for any given atom. And there's three rules which we have to juggle to understand this. The first is the Aufbau principle, the second is the Pauli exclusion principle, and the third is something called Hund's rule. Let's start with the Aufbau principle. The Aufbau principle is pretty simple. We actually kind of already discussed it. The Aufbau principle states that we must fill lower energy subshells before higher energy subshells. In other words, the 1s fills before the 2s, which fills before the 2p, which fills before the 3s, and so on and so forth. We fill our lower energy states before we fill our higher energy states. Note that this doesn't always happen in the same order. There is a weird change when we get to the d orbitals and the f orbitals. Notice that the order kind of switches. If we're filling up our orbitals on this diagram on the right, we would fill the 2p orbitals, then we would fill the 3s, then the 3p, then the 4s, and once we get to the d orbitals, we actually jump back in quantum number. We would go from 4s back to the principal quantum number 3 and fill the 3d orbital. And this is basically because the 3d orbital, it kind of exists at different energy levels depending on what element we're talking about. So this 3d and this 4s, they're close enough in energy. Sometimes they flip positions, but for us, it's important to know or assume that the 3d comes after the 4s. The Pauli exclusion principle, again, we started to introduce this idea, says that there are at most 2 electrons in an orbital, and they have to have opposite spins, which we'll see on the next slide. Basically, one electron spins counterclockwise and the other spins clockwise. And we represent these electrons as either an up arrow or a down arrow to show those opposite spins. Now, real quick sidebar on spins. We would expect if we had 2 electrons, because they're both negative, we would expect them to push away from one another. However, electrons can sort of pair up as long as the partner is spinning in the opposite direction. It kind of minimizes the energy when they're spinning in opposite directions, even though they're the same charge. So if we were to try to put 2 electrons in together, both with the same spin, what would happen is that these electrons would repel one another. So we can't have a situation like on the right here. It has to be opposite spins if they're paired. A couple examples of the Pauli exclusion principle. This first example, where we have one spinning in one direction and the other electron spinning in the other, that's good. We have opposite spins and at most 2 electrons, so that looks like a good orbital. In this case, we're actually violating 2 rules at once. One, there's too many electrons in one orbital, and 2, these 2 down arrows have the same spin, so we can't have that. Our third orbital has 2 electrons with the same spin, so that doesn't work. They're both of the same spin. And finally, we have this single electron. That technically is good. We may end with 1 electron in an orbital. All right, let's talk about our last rule, and this is Hund's rule. Hund's rule states that in any subshell, such as the 2p or the 3d, with multiple orbitals, electrons of the same spin are going to fill all those spots as singles, like you see happening below, before they start doubling up. So take a look at that pattern of how they get filled, and that'll help you in the future as you practice this skill. All right, let's go a little farther with Hund's rule. In any subshell, such as the 2p here, of the same principal quantum number, in this case 2, all electrons are going to have the same energy. So if an electron in a 2px orbital has the same energy as an electron in the 2py orbital. So these will kind of go in side by side because they're at the same energy. So let's construct an electron diagram. The first thing you're going to need is going to be a template, and you can see this follows the pattern of the periodic table. The 1s orbital followed by the 2s, followed by the 3 2p orbitals, and so on and so forth. The second thing to do would be find the number of electrons in your element. I chose as an example sulfur, so we're going to fit 16 electrons in this graph here. 1, 2, the first 2 are paired. 3, 4, the second set are paired. 5, 6, 7, 8, 9, 10. So we're still not there, but we have a full 1s, full 2s, and full 2p. We need 6 more electrons. 1, 2, 1, 2, 3, 4. And that gets us to 16 total electrons for sulfur. Notice if I scroll back, I'm filling this 3p orbital singly and then doubly. Also note that orbitals are separately filled with either 1 or 2 electrons each. We can literally see the 3s orbital has 2 electrons. It has that shape. The 3p orbital is a little more complicated, but basically 1 orbital is assigned to each image at the bottom. Also notice that the Bohr model, for the most part, the principal quantum number shows how that Bohr model would appear. So right now I see I'm ending in the 3s3p orbital, so I should probably draw 3 rings. Now let's take a look at a random set of p orbitals. We want to fill these orbitals up singly before we double them up, just like so. Now, a student came up earlier and asked, why do we not fill the 3s orbital first? And the answer lies in the energy of each orbital. There are 3 2p orbitals, but because they're at the same energy level, they need to be filled singly before doubling up. If we doubled up this first orbital, it wouldn't be the same energy level. It would be at a higher energy level. So we want to fill these orbitals with the same energy with single electrons followed by the doubling. And now let's do a quick Bohr model electron configuration for silicon, followed by the quantum model electron configuration. Since silicon has 14 electrons, doing this Bohr model first, we put 2 in the first row. In the second ring, 1, 2, 3, 4, 5, 6, 7, 8. We have now a total of 10 electrons. And in the third ring, 1, 2, 3, 4. And that gets us to the quantum model electron configuration for silicon. Now let's try filling in this quantum model down below. In the 1s orbital, we have single double. In the 2s orbital, we have single double. In the 2p orbital, we have single single single, and then double double double. We're currently at 10 total electrons, so we need 4 more. The 3s fills single double, and the 3p fills single single. And that's it. If you look closely, you may see something that's different between our two models. And that's what we're going to check at the end of our practice for today. All right, I hope this video helped you understand the quantum mechanical model and how electrons fit into its different parts.